Okay, so I'm going to talk to you a little bit about the volume of a sphere. And this is what I like to call one of those blow your mind lessons. Because probably you know by now that the volume of a cylinder is the area of the base times the height. You also know that the volume of a sphere is 4/3 pi r cubed. Now you sort of looked at that website that talked to you about why the pyramid and the cone are 1/3 the volume of a prism, but I doubt that you have really seen a good explanation, besides maybe pouring water back and forth, about why a sphere is a 4/3 of, where that 4/3 comes from, and why our cubes sort of make sense, I think, to everyone, but where the heck does that 4/3 come from? So let's take a look. Now, you read a little bit about Cavalieri's principle, which says that if I have two shapes, and at every cross-section, those shapes have equal area. Every cross-section is equal area. So let's say I pick, this very middle portion of my sphere, and I pick this very middle portion of my cylinder. Those, I think we can tell, since I labeled this R and I labeled this R, that those cross-sections would be the same, right? I'd have a perfect circle here with radius of R, and I'd have a perfect circle here with radius of R. The cross-sections would be the same. However, you sort of notice that here, as I look at the different cross-sections, they're going to stay the same all the way up and down, right? They're always going to be a circle with radius of R. But if I come over here, and we've got this sphere, I'm going to angle this a little bit more that way so you can see a little better. If I've got that sphere, I can see that if I look at another cross-section, say I look at this cross-section up here, it's not a very good circle, then, this is not the same as R, right? This is a smaller radius because the sphere is kind of coming up and closing off to a point. But if I found a shape that always had the same cross-sectional area as a sphere all the way up and down, then I could show that those two shapes must have the same volume. And that's really what Cavalieri's principle was saying. Now, this shape isn't going to do it, but I'm going to do something a little funky. And this is what's going to take the most creative, mathematically minded parts of you. What I'm going to do is I'm going to pretend like this is made out of clay or something. And what I'm going to do is I'm going to cut a cone out of the top, and I'm going to cut a cone out of the bottom. All right, so this sounds a little crazy. Just bear with me. It's going to end up looking something like this, but what I need you to recognize is that the only piece that I still have is sort of this outer piece, right? So I have kind of like a little hole in the middle there. This is all dug out. So I have a hole in the middle down that center of the cylinder, and I have a hole right here that I pulled out of the bottom of the cylinder, but I still have these kind of side pieces of the cylinder coming out in front and going out behind. So I hope that sort of makes sense. I was trying to kind of find a picture of this on the internet, but okay, so this is hollow, but around here the cylinder is sort of filling this out. So imagine that you took a can that was filled in and kind of pulled out a cone on the top and pulled out a cone on the bottom so that the apex of the cone were touching each other. So we've got that much. Well, now look at some patterns. Notice what happens to the cross sections. If I'm looking at this big cross section, I only have the cone sticking out one little point, so that won't affect my whole circle, right? A point takes up no space. But if I look right here, well, now I have kind of my cone is going around here, my cylinder is going around here, so what I really kind of have is something that looks like that, where I've got kind of an oval, right, because there's a little hole for my cone. So I have like a donut. Well, what that means is that the area of this donut is going to be a little bit smaller than the area of that big circle in the middle of the cylinder. Good? Now over here, look, that's the same thing that's going to happen here. As I go up a little bit more, I'm going to get a smaller radius. I'm going to get a smaller cross section. If I go all the way to the top, well, I've dug the whole top of the cone out. And so I'm actually going to have no area whatsoever on this very, very top level, which would be the same thing here because that's going to end just at a point, and this is an open circle. If I go down a little bit further, I wish I had a little bit more than just black and red so you can see this better. But I think it'll be cool if you get it. Let's see if we can kind of go up this high. So we want to go like right here. So we're going to kind of come across and say, we were here on our sphere, we want to be here on our cylinder. And let's make that dot a little bit smaller. I'll make this a little bit smaller too so that this all makes sense. Okay. So we want to kind of pull out the same cross-sectional area so that those are the same distance from the radius. So we're going to go up some kind of arbitrary amount. We'll call it x. Okay? Now here's going to be the very center of our cylinder, and you recognize that I did make the height of the cylinder 2 times the radius, and that means I'm going to have the same top to bottom distance on both shapes. Okay, so I'm picking some point that is sort of x above. I'm going to let that be x. And what's going to happen up there? Well, I'm going to have kind of my open circle where the cone is pulled out, and I'm going to have the circle I still have left. That is the part of my cylinder. So what are we doing here? What we want to do is show that even if this is just x, right, this is kind of an arbitrary height above the center, if we could show that for some arbitrary height x, this cross-section is the same as this cross-section, then we have really just shown that for every cross-section, no matter where it is, because we picked x, so it could be a positive x, a negative x, it could be this direction, it could be that direction, right? And it could be a little bit or a lot. If we pick x and show for one cross-section the volumes are the same, or the areas are the same in the cross-sections, then that shows that for all cross-sections, the area is the same, and if for all cross-sections the areas are the same, Cavalieri's principle tells us we have equal volumes. So we want to compare this ring with this circle. Oh, and circles and rings are something you'll do in calculus as well. So let's think. We've got our ring. Now remember, this is should be a perfect circle, right? We're looking at a cylinder. It just looks smushed because I'm on the board, right? So it has to be smushed. So maybe I need to make it smaller so I have room for both. So we've got our ring for the cylinder, and we have our circle for the sphere. And we need to figure out what's the area of both of these. Okay, what's the area of both of those? Once we find the area, sorry, I'm kind of like going out and in. This is a really old school video compared to all the beautiful ones that are on YouTube. So we have to figure out the area of both of these. Okay, well, we know the area of a circle is going to be pi r squared. Well, what's the radius of the circle? We've got to figure that out, right? The area is going to equal pi r squared, but we don't know what the area is. And we're already using r, so is it r? Well, we talked about that, right? It's not r. Because over here, when we're looking, this is r. So what's this little piece? How can I represent that? How can I represent that? Let you look at it. I could give it a different variable, but I actually don't want to do that. I'd like to keep everything with x's and r's because that's what I'm using over here. And so if I can keep them both in x's and r's, then I can find a relationship. All right, here's the magical part here. If I were to draw a line segment from the center of the sphere out to this point, well, where is this point? This point is on the sphere. What's the distance from the center of a sphere to the sphere? It's the radius. So this right here, that line right there is r also. And now we drew these perpendicular, so that's a right angle. So I know two sides of a right triangle, and I'm looking for the third. And so whenever that's happening, then we're going to use Pythagorean theorem. So we know that this last side is going to be, well, let's see. We know that, our x squared plus our side that we're looking for
or our segment squared is equal to r squared. And so then that means that our segment squared is equal to r squared minus x squared. So our segment here, the radius of our cross section, is the square root of r squared minus x squared. Good? R squared minus x squared and the square root. So I'm going to come back over here and we're going to write that in. The square root of r squared minus x squared. Okay, now let's think about our ring.